We just finished conservation of momentum for collisions in a single dimension. Now we're going to take a look at what happens when we have to include multiple dimensions. You'll notice here that we only go up to 2 dimensions. And the reason for that is really a 3-dimensional collision isn't all that much more complicated when you think about it. The collision usually lies in some plane as long as we're dealing with 2 different objects. So we'll look at our collision, multiple dimensions. We'll look at the perfectly inelastic collision first. Then we'll see some of the difficulties that we run into when we try to do a 2-dimensional elastic collision. So just to remind ourselves of where we are here, we can look at conservation momentum. Because momentum is a vector, it has to be conserved in all directions. So our equation for conservation momentum, of course, says that the momentum before a collision must be equal to the momentum after the collision. We envision 2 objects coming together, interacting with one another via a collision, and then going out with the same total momentum that they came in. So we can write this equation in 2 dimensions as 1 conservation of momentum in the x direction and 1 conservation of momentum in the y direction. This is the general case. This occurs for both elastic and inelastic collisions. This will be true. Now, for the completely inelastic or the perfectly inelastic collision, we can reduce this by saying that 2 bodies come in, a single body will leave. In this particular case, because both bodies after the collision have the same velocity, the conservation of momentum equations reduce to these simpler forms right here. So this actually reduces the number of variables we have, and oftentimes will reduce the number of unknowns that we need to find. Let's talk about the inelastic collision in 2 dimensions, where the 2 bodies stick together, what we call the perfectly inelastic collision or completely inelastic collision. In this case, we're going to have a very simple case. We have a car traveling in the x direction at 25 meters per second. We have an SUV traveling in the y direction at 20 meters per second. We've basically replaced east and west and north and south with x and y respectively. Now, the car has a mass of 1,500 kilograms, whereas the SUV has a mass of 2,500 kilograms. After they collide, we try to see and what the final velocity is of these 2 cars when they're stuck together. Now, again, of course, we're only interested in the actual collision. Friction and other forces that are acting on the vehicles are ignored for this case. Friction will bring the vehicles to rest following the collision, but we are looking at, again, what is V final immediately after they interact and they lock together. So once again, we look at our initial conditions to see what is happening before. Again, this is a very convenient way of doing this because the car only has x momentum and the SUV is only going to have y momentum. So we calculate the car's momentum before, 3.7 times 10 to the 4 Newton seconds of momentum, again, going in the x direction. Okay, that's 1,500 times 25 meters per second. Now we look at the y momentum of the SUV. In this case, the y momentum of the SUV is going to be its mass times its velocity in the y direction. Again, note that there's no momentum of the first car in the y direction, as there was no momentum of the SUV in the x direction. And so the total momentum before the collision for the y direction is going to be 2,500 times 20. So that gives us a total momentum of 5 times 10 to the 4. So looking back at what's happening, once again, I have momentum in the x direction, completely taken up by the car's momentum, momentum in the y direction, completely taken up by the momentum of the SUV, and essentially I'll have 2 different equations here. Now, the total mass of the system after the collision takes place is 4,000 kilograms because essentially the car and the SUV will lock together and act as one body. So all I really need to do here is say, okay, what was the momentum of the system before the collision in the x direction? What was the momentum of the collision after? If I take this momentum and I divide by the mass, I will get the velocity in each direction. Again, we don't write this out explicitly, but going back to this equation right here, again, here our first vehicle had momentum in the x direction, the second one did not. So this is our momentum. It is going to be equal to the sum of the masses times the final velocity. The car had no momentum in the y direction. The SUV had all the momentum. So the total mass times the final velocity will be related to that momentum. Okay, let's go back here to our results. And again, here's my x velocity, here's my y velocity of this combined mass. And of course, that gives me all my unknowns. Now I know how fast in the x direction, how fast in the y direction, and there's nothing really else to know about this collision. Additionally, I could find out the final speed. Of course, we can use the Pythagorean theorem to find that. I know the x and the y components, so a different way of looking at this is, what is the total magnitude of the velocity after the collision? And that can be obtained this way, given the x and the y components. All right. And what is the final momentum, magnitude, of course, of the two vehicles? And that's given here too. If I want the angle that the two go off, again, two basic ways we can express a vector in two-dimensional space is in terms of its x and its y components, or its orthogonal components, or we can express it in terms of magnitude and the angle with respect to the x-axis, if we're using the x-axis as a axis of reference here. So we can see that by using inverse tangent, we can find the angle with respect to the easterly direction, which happens to be x in this case, and that's 53 degrees. So again, very simple interaction that takes place here. If we had these coming in at an angle, I could still solve for this. As long as I know my initial conditions, I can find my final velocity in the x and y direction. I can find the final magnitude of the velocity and the angle at which the two objects are traveling. So it's a fairly straightforward problem. It's exactly like our problem in one dimension, except for we have two equations and typically two unknowns. Again, looking at the vectors before and after, here is the vector for momentum in the x direction. Here's the vector for the momentum in the y direction. If we add this vector to this vector, we get a final vector that equals my momentum after the collision is taking place. And what's important here to note is this final momentum is actually also the initial momentum. This vector right here at a 53-degree angle, I believe it was, okay, at 7.08 times 10 to the 4 Newton seconds was the momentum of both vehicles before and after the collision. Okay, let's talk about the difficult problem. When we go to two dimensions for an elastic collision, a perfectly elastic collision, we add another equation to our system of equations. Now, here is our equation for conservation of momentum in the x direction. Here's our equation for the conservation of momentum in the y direction. And basically, this will hold true for all collisions. What is different here is now I have a conservation equation for kinetic energy before and after. And this, again, is a specialized case where all the mechanical energy before is equal to the mechanical energy after. For macroscopic systems, we always lose a little bit of mechanical energy during the collision. So we do get cases that approximate this macroscopically, but it's really just microscopic collisions where we would truly conserve this. But it's a good approximation for quite a few interactions. The problem that happens here, and if we look at the equations, we can clearly see that this new equation adds velocities to the second power. That makes it difficult to combine with these two equations right here. Oftentimes, when we're solving a system of equations, we can use linear techniques to combine the two. Unfortunately for this, this is a non-linear equation. We don't have the same power of velocity as we do in the first two equations. So solving this becomes a little bit tricky. At best, sometimes we can hope to create some type of quadratic relationship between the two and solve for the roots, but oftentimes we'll need a numeric method to find this. So again, this type of setup where we have a perfectly elastic collision and we're trying to find unknowns is a very difficult problem that has to be set up in such a way that it's solvable. So I'm going to take a look at a collision where we have all the momentum in the x direction with one particle coming in. It interacts with the second particle. And the unknowns here are the angle at which the second particle goes out and the final velocities of these two. Now, again, this doesn't seem too bad of a problem. If we go back to our equations right here, we say, oh, we have three equations. We have three unknowns. We don't know this final speed. We don't know this final speed. We don't know this angle. But even though it seems like I've really simplified this problem, we're going to find out that it isn't simplified enough to make this easily solvable. So let's go ahead and do this. We can take into account that the only momentum we have going into the collision is from this first mass, M1, and that the momentum before is equal to the momentum after in the x direction. The momentum of this first particle is going to be 0 in the x direction, and we have the momentum of the two particles in the y direction afterward. The blue particle is going to have a positive x momentum. The yellow particle is going to have a positive y momentum. The yellow is going to have a negative y momentum here. Okay, that'll cancel out. They'll balance to be equal and opposite. Okay, so again, we use conservation of momentum. We are going to put numbers to this particular system and solve for the unknowns that we can. Again, remember, these are the three equations available, and this nonlinear relationship is where we're going to run into a bit of a problem. Once again, M2 is not moving, so I can eliminate that from the first equation. So we do conservation of momentum in the x direction. Now, we're going to say that we know theta, but we don't know phi here. So when I actually put my numbers here, I'm going to replace V1x final with V1 final cosine theta, because the x component is the cosine theta times the overall magnitude. I'll do the same thing for this. Again, phi is unknown, and we have M2 V2 cosine phi is the same as M2 V2 x final. So here's my first equation for conservation of momentum in the x direction. Okay, I'm going to do the same thing for the y direction. The y direction, the left-hand side of the equation is 0 because neither particle is moving in the y direction before the collision. As we said, the momentum is going to be equal and opposite in the y direction afterward. We put in sine theta and sine phi to get the y components of V1 and V2 respectively, or M1 and M2 respectively. And we get this relationship right here for the y direction. So far, it seems pretty good. We have a relationship between my unknowns here, V1f, V2f, and phi. And we have a relationship here between V1f, V2f, and phi. All right. Now we're going to get our third equation. We're going to do conservation of kinetic energy. And we say that the kinetic energy before is equal to the kinetic energy after, which only occurs for a perfectly elastic collision. So I can multiply both sides of the equation by 2. That gives us this equation right here. And here's our relationship between our initial velocity of our particle and our final velocities of the two particles. Now, here's where it gets a little bit tricky. And again, I have three equations right here. I'm going to put numbers to this, and we're going to see where we can go with this. Now, let's have this come in at 20 meters per second. Let's have M1 at 5 kilograms. Let's have M2 at 8 kilograms. I'm going to make this a little more massive. I'm going to say, what happens when V1F leaves at a 30-degree angle? Now, it's important to understand here that depending on how these two particles are interact, if they interact at straight on, it's really a one-dimensional collision. I wouldn't have had to go through all of this. We'd revert back to what we had in the first case. But as they come in, okay, and it becomes more and more of a glancing collision, this M1 is going to go off at a steeper and steeper angle. So really, I need to have a known here. I need to know what angle this is going off on to know what is going to happen to this particle right here. Okay, so here are the numbers plugged in to all three of our equations. Typically, when we have three equations and three unknowns, we attempt to solve for the unknowns. And we simplify this a little bit to get this expression right here. And it seems like we're doing okay. But the problem that we have here is, again, the sine phi and the cosine phi really make it difficult to substitute that into this equation with our square of our velocity. Again, in some situations where we know the angle's going out, we could actually find, we could set up a quadratic and we could solve for the roots for this. But for this particular case, there really would need some elegant solution to this to solve for this, and it's beyond my abilities for this. So you can just do this numerically, and really all you can do sometimes is graph these different equations, see where you get agreement, see where you get intersections, and try to find it that way. I just used a simple numeric method to find out the unknowns here. And again, these problems are really, really difficult because of all the fact that we're dealing with a nonlinear set of equations. So more realistically, if we look at a collision, we would probably want to look at something where we have two unknowns rather than three unknowns, and we don't have to resort to conservation of energy, because that's where our problems come in. So we look at the momentum before and we look at the momentum after. Here we can see the momentum of the first particle coming in. The first particle going out is going off in this direction. The particle going out is going off in this direction. And again, even if you attempt to solve this, I guess, via a graphical method, you're still not going to be able to get an obvious solution here, because even at 30 degrees, you could keep extending this vector out to find P2F, and you wouldn't have a unique solution unless you used conservation of energy for that. So we're going to look at a simpler case. Now we're going to restrict how this works, and we're going to get rid of that problem that I had with phi here. We're going to say, we're going to really make this simple. We're going to make two of the particles the same mass, which is actually not all that uncommon for collisions of elementary particles. But we're going to have this come in at 3 meters per second. Both particles are going to go out at the same angle. The white will go up at 45 degrees. The red will go down at negative 45 degrees. And we want to know what the final velocity here is and what the final velocity here is. And you can see what we've done here. We've essentially set this up so that we have two unknowns, so we only need to apply two equations here. You can actually solve this without using conservation of energy, although you'll see in a second what I do here. Okay, so once again, all the momentum initially is in the x direction, so that is the only part that remains here. These other terms disappear. The red ball is going to have no momentum initially, so MB, VB, IX and MB, VB, IY are both zero. And of course, MA has no momentum in the y direction. So we set these equal to this. We also say that they have the same mass, so I can get rid of this mess where we have MA and MB. Now we have two equations that reduce to this, and it seems pretty obvious. MA is going to come in with 3 meters per second, but in the y direction, if they're both the same mass and they both leave with equal and opposite momenta, each of these are going to leave with the same velocity. Okay, so now I again plug in numbers. Again, this equation becomes pretty obvious that VA equals VB. The sine of 45 degrees is 0.707. The sine of negative 45 degrees is negative 0.707. And of course, that just again proves to us that VA equals VB. So this equation gives us one of our relationships, that these are the same. Now I'm going to use this one right here to find out what the relationship is. Not really what the relationship is, what VA and VB actually are, because now they're just V, they're the same quantity. And here, again, we have 3 meters per second. I have the momentum of the first in the x direction, the first ball in the x direction, the momentum in the second direction divided by the mass. Of course, that just becomes a fraction of the final velocity. I add the two together, and then I solve for V. They both leave at 2 meters per second. And if you check this, this will actually agree with conservation of energy. So what I've essentially done here is ignored one of the characteristics of this. Even though it's perfectly elastic, I'm ignoring the energy here in order to make this problem a whole lot easier to solve. So again, just basic procedure for solving these. Set up your coordinate system. Notice how I set up the coordinate system in each of these cases. Here I had all the initial momentum in the x direction. For this case, I had all the momentum in the x direction for this case. And in the other case, where it was an inelastic collision, the axes were set up really, it was convenient because they were both coming in at a 90-degree angle with the x and y directions. It just makes all your calculations all that much easier, because by making all the momentum in the x direction initially, notice how my y conservation of momentum became very simple. It was just equal to 0 there. Diagrams, always sketch it out so that you can visualize what this should look like. Okay, what I try to do is run a simulation in my brain as to the way I think this is going to behave, and then I draw a sketch that would go along with what my intuition is telling me. It also helps you identify what you know and what you don't know for this particular case. I knew the angles, I knew the initial momentum, but of course, obviously, I didn't know how fast they were leaving, so those were my two unknowns. Conservation of momentum occurs for all cases. You're going to conserve momentum in the x direction and the y direction. And again, if you set up your coordinate system the right way, you can make these equations as simple as possible. And of course, if we have perfectly elastic collision, then we can use conservation of mechanical energy. But again, this often creates a difficulty. So many times these equations, or I should say, these setups will be put together in such a way that they're easier to solve, and we're not dealing with a mess of a system of nonlinear equations. Again, solve the equations simultaneously, and again, there will be two equations for the two-dimensional inelastic collision, where the V final is the same for both particles, and three equations for the elastic collision. And of course, that will hopefully give you your unknowns.